Welcome back to the deep dive. We're here again to really dig into the source material you've shared and pull out the key insights.
Yeah, happy to be here.
So today we're tackling a pretty deep topic in AI sequence modeling. This is the technology behind so much stuff we see now, language models obviously, but also computer vision, time series analysis.
Pretty fundamental stuff, and we're zeroing in on a brand new paper, one that proposes a really interesting new angle for building these models more efficiently, more powerfully.
Right, this paper, Improving Bilinear RNNs with Closed Loop Control, and the model itself is called Comba.
That's the one, Comba.
We've got your notes, highlights from the paper, bits of related research they mention. And our goal really is to unpack the academic side, focusing hard on the core innovations. What makes Comba different?
Exactly. This is kind of your fast track to grasping some pretty cutting-edge thinking in AI architectures.
And they set a fascinating tone right at the start, don't they, with that Confucius quote?
Oh yeah, learning without thinking misleads. It's a great framing device. They're basically saying these models can't just absorb data passively. They need some mechanism to actively process, to control how they learn and remember from a sequence. It really sets the stage for their whole approach.
A philosophical underpinning for the tech. Love it. Okay, so before we get right into Comba, maybe we should sketch out the landscape a bit. Where does sequence modeling stand right now?
Good idea. Well, the elephant in the room for a while now has been the transformer, based on softmax attention.
Revolutionized everything, really.
Absolutely. Fantastic at parallel processing. It looks at the whole sequence at once. And things like the KV cache help it manage context pretty well for, a lot of tasks.
But there's always a but, isn't there? What's the downside?
The big one is scaling. The way attention works, the compute cost, and the memory needed, they grow quadratically with the sequence length.
Right, so double the length, quadruple the cost, roughly speaking.
Exactly. So when you get to really, really long sequences, think long documents, high-res video transformers just become incredibly expensive, sometimes just not feasible.
And that bottleneck, that's what pushed people to look for alternatives, more efficient methods.
Precisely. That led to this whole wave of research into what people call linear RNNs, or sometimes state space models, SSMs. You might have heard of Mamba or GLA.
Yeah, those names ring a bell. What's their core idea?
Efficiency, especially at increment time. They process the sequence step by step like traditional RNNs, but the goal is constant memory and compute costs per step. O1 complexity, basically, no matter how long the sequence gets.
Okay, so O1 inference. That sounds much better for long sequences. How do they manage the memory side?
They compress everything they've seen so far into a fixed size state, like a summary. Then, as new input arrives, they use these learned gates. Alpha and beta are the usual terms to decide how to blend the new information into that existing state.
Sort of like updating your mental summary as a conversation goes on.
Yeah, that's a decent analogy, but the paper we're looking at points out a key limitation with these linear RNNs.
Which is?
Their memory management, while efficient, is often described as heuristic or unsupervised. There's no direct signal telling the model, hey, remember this specific fact from way back when. They tend to just average things out or forget information uniformly over time.
Uniform forgetting, so less like pinpointing a specific memory, more like everything just gets a bit fuzzy.
Kind of, yeah. It lacks that targeted control over what stays and what goes. And that brings us to the next step in this evolution. Bilinear RNNs, that's the category Comba fits into.
Okay, Bilinear RNNs, what's the crucial difference there?
The key leap is introducing interactions between that recurrent state, the memory, and the incoming data, specifically its key vector. It's not just adding new stuff to the state, it's a more complex, bilinear combination. And this structure allows for supervised memory management.
Supervised memory, so the model gets taught how to remember.
Exactly. The mechanism often involves something called the delta learning rule. Instead of just hoping the right stuff sticks, this rule gives the model an explicit objective. Think of it like feedback. Your current memory, combined with this input, should have produced X, but it produced Y. Adjust your memory like this to fix it.
So it's learning to correct its internal state based on errors it makes, targeting the update.
Precisely. It moves beyond that uniform passive forgetting. The paper mentions others in this family, like Gated DeltaNet, RWKV7.
Right.
And these bilinear models tend to hit a sweet spot. They're more expressive than the purely linear RNNs because of that state-input interaction, but they can still often be trained efficiently using parallel techniques, unlike some of the newest, very complex, non-linear RNNs, which sacrifice some of that training parallelism for even more power.
Okay, got the picture. Transformers are powerful but scale poorly. Linear RNNs are efficient but have fuzzy memory. Bilinear RNNs add targeted, supervised memory control. So now, finally, Comba, What's the big idea here that sets it apart even from other bilinear RNNs?
The absolute core concept, the thing they really hang their hat on, is designing Comba using principles from closed-loop control theory.
Closed loop control. Okay, that sounds like it's borrowed from engineering or robotics, maybe?
Exactly, that's the perfect connection. In control systems, an open-loop system just runs based on input. It doesn't check its own output. Think of a simple timer on a microwave.
Set it and forget it.
Right. But a closed-loop system measures its state or output and uses that measurement, that feedback, to dynamically adjust its actions, like a thermostat reading the room temperature to turn the heat on or off.
So Comba is built to constantly monitor itself and adjust its internal processing based on feedback.
That's the idea. They argue this makes the system much more adaptable, more robust, especially when dealing with complex, changing data streams like long sequences. It's designed to be, as they put it, a strictly closed-loop system.
That's a really powerful theoretical shift. How does this closed loop thinking actually show up in the model's architecture? What are the specific innovations?
Okay, let's break down a few key ones. First, there's how they structure the state transition, how the memory updates. They use something called scalar-plus-low-rank, or SPLR.
SPLR. What does that actually involve?
Basically, the update rule involves a simple scalar multiplication across the state, plus an adjustment term that's low rank derived from the input's key vector. It's a specific mathematical form they chose for the update.
How does that compare to, say, Gated DeltaNet or RWKV7?
They used different forms. Gated DeltaNet used IPLR involving the identity matrix. RWKV7 used DPLR with a diagonal matrix. Comba's SPLR is, in a sense, structurally simpler.
And the benefit of this simpler SPLR structure?
Well, empirically, they found it hit a sweet spot. It's expressive enough to learn effectively, but it gave them a big boost in pre-training speed and significantly reduced memory usage compared to RWKV7, like halved it.
Wow, half the memory just from that structural choice.
Seems so. Plus, they note SPLR naturally allows for negative eigenvalues in the state transition matrix, which some recent research, they also found the IPLR form sometimes led to overfitting, so SPLR seemed more stable.
Interesting. Simple math leading to better practical outcomes. Okay, what's the next big closed loop innovation?
This one is maybe the most direct expression of that control theory idea. Comba uses two-stage closed-loop feedback.
2 stages, not just one feedback loop.
Right. Some earlier bilinear models might have feedback influencing the state update, but Comba applies correction at 2 points. Stage 1 is state feedback. Before the new input fully updates the memory state, the model uses its current state to slightly.
It's like, based on what I already know, let me tweak this new data slightly before I store it.
Exactly. Then stage 2 is output feedback. After processing the input and updating the state, when the model is about to generate its output, it applies another correction. This one is based on the relationship between the query, what it's trying to answer, and the key related to the input it just processed. They specifically highlight this output correction term.
So it refines the answer just before giving it, based on how relevant the input was to the implicit question.
That's a good way to put it. From an optimization angle, it encourages query key similarity. From a memory angle, they suggest it helps ensure information is stored clearly and can be retrieved accurately. And this two-stage setup, especially the output correction, apparently makes a big difference, lower perplexity, much better memory, and recall performance.
That makes sense. Correcting both input processing and output generation seems powerful. They mentioned a little detail about initializing a parameter D in that output correction.
Yeah, that was a neat finding. For smaller models, like 340M parameters, they initialize the CD value very small, 0.02, but for a bigger 1.3B parameter model, they initialized it to 1.
Why the difference?
Their guess is that smaller models are just more fragile early on, more easily pushed in bad directions by gradients, so starting the correction strength low prevents instability. Larger models are more robust and can handle the stronger initial correction signal.
Fascinating how these subtle details matter. Okay, what else? Any other key innovations?
Yes, one related to handling time and memory, forcing the model to learn how to forget.
Forcing it to learn. How?
Similar to another model, Mamba 2, they initialize the forget gate, the part deciding how much old memory to keep very close to 1, meaning initially it tries to remember almost everything. The input gate is initialized separately.
Wait, why start by remembering everything? Isn't forgetting important?
It seems counterintuitive, right? But the logic is, if you start with a default tendency to forget quickly, the model might never learn to hold on to information for truly long durations, especially if trained on shorter sequences. By starting near remember all, the training process forces the model to actively learn when it's beneficial to forget something, rather than just forgetting passively.
So it has to explicitly learn the value of forgetting rather than just decaying memory. Active learn forgetting.
Exactly, and they argue this is crucial for length extrapolation, getting the model to work well on sequences much longer than it ever saw in training. It's about learning robust memory management over time. They also add a constraint to make sure the feedback doesn't become too strong and cause overfitting.
Learn and forgetting for long sequences. Very cool. Okay, we've covered theory, structure, memory. What about making this thing actually run fast?
Right, the practical side, that's the last major innovation, hardware efficient, chunk-wise, parallel kernel.
Okay, unpack that. RNNs are efficient at inference, right? Oh, one.
Correct. Once trained, they're fast to use. But training them can be slow if you do it naively. The step-by-step recursive nature doesn't map perfectly onto modern GPUs, which love big parallel matrix multiplications.
So fast to use, slow to train, that's a problem for building big models.
A major one. So the Comba team put a lot of effort into building a custom computation kernel using Triton, which is a language for writing highly optimized code for GPUs. Their kernel implements chunk-wise parallelism.
Meaning they can break the sequence into chunks and process them partly in parallel during training?
Yep, overcoming that sequential bottleneck.
And what was the payoff for all that optimization work?
Pretty huge, actually. Figure 3 on the paper shows something like a 40% speed up in the forward pass compared to Gated DeltaNet, another bilinear RNN.
40% faster, just on the forward pass. That adds up incredibly fast during training.
Absolutely. It makes training modis at scale much more feasible.
How did they squeeze out that extra speed? What were the tricks?
A couple of key things. They found a way to compute an inverse matrix needed for the parallel chunking more efficiently only once per chunk versus twice in Gated DeltaNet. They also used some specific mathematical representations like the WY representation and UT transform to minimize the amount of computation that isn't fast matrix multiplication.
Clever engineering meeting clever theory. Okay, so putting it all together, closed loop control, SPLR, two-stage feedback, learn forgetting, Triton kernel. How did Comba actually perform on benchmarks?
The results look quite strong across the board. That 40% speed up we just mentioned, Figure 3, is a big win for practical efficiency. It holds its own against other efficient models, and while something like flash attention is faster for very short sequences, Comba's linear scaling makes it win out as sequences get longer.
Makes sense. What about standard language tasks? Perplexity, reasoning?
On language modeling benchmarks, Table 6, Figure 4, it generally achieves lower perplexity, and it consistently does well, sometimes better than competitors, on common sense reasoning tasks. The authors speculate that the recursive structure might inherently lend itself to a kind of step-by-step reasoning like chain of thought.
And they tied performance back to those innovations.
Definitely. They credit the output correction mechanism specifically for helping reduce perplexity and boost performance on memory and question answering tasks. And they confirmed their SPLR state transition consistently outperformed the IPLR DPLR alternatives. The training loss curves, Figure 4, also show Comba reaching lower loss faster.
Okay, reasoning looks good, but what about raw recall? That's traditionally been a weak spot for RNNs compared to transformers looking at the whole sequence.
This is a really significant finding. The paper states Comba achieves recall performance very close to that of transformers. That's a big deal, overcoming a classic RNN limitation.
Wow, closing the recall gap. How?
They attribute it heavily to that two-stage feedback system, particularly the output correction, really clarifying how memory is stored and retrieved. They even designed a synthetic test, MQAR, Figure 5, where bilinear RNNs like Comba got perfect recall. And interestingly, they also showed hybrid models mixing Comba with a bit of traditional softmax attention could sometimes even outperform pure transformer models, Table 7.
Very impressive on the recall front. What about really long sequences, like in the long bench tests?
On long bench, Table 8, Comba generally performed very well, often leading the pack, especially on things like question answering and few shot learning tasks within long contexts.
But not always the absolute best.
Right, they're quite transparent about this. On tasks like summarization or code generation within long context, Gated DeltaNet sometimes edged it out slightly. They acknowledge this needs more digging to fully understand the nuances, but they did confirm that turning off their specific initialization tricks like the learned forgetting setup hurt performance on these long tasks.
Good to see that nuance reported. Did they test it outside of language? You mentioned vision earlier.
Yes, and that's another strength versatility. On ImageNet classification, Table 9, it showed state-of-the-art results for the efficiency-accuracy trade-off. And maybe even more compellingly, on object tracking tasks like GAT10K and LaSat, Table 10, it performed exceptionally well.
Object tracking. That really requires understanding dynamics over time.
Exactly. Capturing those long-range temporal dependencies is key, and Comba's architecture seems really well suited for that kind of dynamic sequence processing. Seeing it work well in both language and vision really validates the core principles.
Strong performance across domains. Now, no research is perfect. What limitations did the authors themselves point out?
The main ones were practical constraints. They didn't have the massive compute resources to train models beyond the 1.3 billion parameter scale, so they couldn't directly compare against, say, the very largest state-of-the-art models out there.
Makes sense.
And they also couldn't directly benchmark against some of the very latest but proprietary or closed source nonlinear RNNs like Titans or MIRS.
Understandable hurdles in academic research. And what are they planning next?
They mentioned wanting to push the chunk-wise parallelism further, potentially enabling even more complex nonlinear models to be trained efficiently. And they're interested in exploring more sophisticated hybrid architectures, maybe combining Comma's ideas with other techniques like gated slot attention.
Okay, so let's wrap up this deep dive. Comba really feels like a substantial step. It's taking established bilinear RNN ideas and layering on this quite fundamental concept from control theory, the closed-loop feedback.
Yeah, it's not just tweaking parameters, it's a conceptual shift combined with some very clever concrete innovations. That efficient FPLR structure, the two-stage feedback, the learned forgetting, and crucially, the practical Triton kernel that makes it trainable.
So hopefully you listening now have a much clearer picture of the cutting edge in efficient sequence modeling. You've got a handle on bilinear dynamics, supervised memory, why feedback loops matter, and how implementation can be just as critical as the theory.
It really highlights how ideas from other fields, like control theory in this case, can cross-pollinate and lead to genuinely new approaches in AI design.
Which brings us to our final provocative thought. Comba demonstrates powerfully how feedback loops and dynamic correction, inspired by control theory, can improve sequence processing and memory in AI. So the question is, could this core idea, designing systems with explicit feedback mechanisms to constantly refine their internal states and outputs, become a fundamental principle for building other kinds of neural networks in the future, maybe even ones that don't deal with sequences at all?
That's a fascinating question. The idea of a system learning to actively regulate and improve itself based on its own internal processing, that feels like it could have implications far beyond just reading text or watching video, doesn't it? It makes you wonder how much self-correction we might want to build into AI learning processes more broadly. Definitely something to think about.